Hi, welcome to the ICTS String seminar. So today we have Mukhopadhyay from IIT Madras. Will be talking to us about black hole complementarity from microstate model.
Okay, so thank you for having me here. So I think it's good to have some watch around. Okay, all right. Okay, there is one there. Okay, so yeah, thanks again for having me here. It's wonderful to be here. And today I will be talking about some of the things that I have been working on for 2 years, but we recently started understanding it a little bit better. So today the plan is, okay, I can do it from here. This is not working. No. Neither is, now this one is working. Okay. Okay, so the plan is that I will give a very superficial motivation to black hole complementarity and motivate why we need microstate models in the first place. So this will be rather short and brief motivation. Mainly what I will try to motivate is that we need some toy model, at least to understand how information can be copied twice, one in the interior of the black hole and the other from the exterior point of view. It can be accessed from 2 different ways without violating seemingly anything about quantum mechanics and all. And then I will talk about 2 toy models where this is possible, but I see it's not yet a microstate model. And this is not yet published work, but we have concrete results. I'll try to show these 2 models, and especially by the trumpet, I mean JT gravity, using this terminology of Clifford Johnson, who created this nice trumpet-like image for JT black hole. And then I will talk about a simple microstate model which incorporates these kinds of insights, but that will be firstly at some classical level. And then I will talk about including this evaporation process and show how some of what insights in these toy models are actually replicated. And then I will end with some conclusions and outlook. And this work will be, most of the talk will be based on some recent work I'm doing with my student, Tanay, and my colleague, Prabha. I have learned a lot of quantum information theory from her, and my other students, Sukrut and Hariram. And one of these works have already come out about 2 years ago, and we have also written some review of, which is now a highlight in EPJC, where we have also reviewed this microstate, why we need microstate models and some of this black hole information paradox. But the main focus of the review was bulk reconstruction. And so there we have given some perspective on this. So I'll start with the motivation, which I now say I admit it is very superficial, so it should not, this should be quite standard, but I just simply go for the sake of completeness. So the black hole complementary principle actually is a old idea given by Susskind, Thoraclius, and Uklum in 1993, and it was basically motivated by some earlier work by Tooft using some brick wall model, and these came up with this idea that the way to resolve the black hole information paradox, you need a double copy of information. So one is accessible by the infalling observer. A copy of the information is available by the infalling observer of the initial state that formed the black hole. And another copy will be accessible to the outside observer who will access the Hawking quanta coming out of the black hole. And there will be no real problem because no real problem with the no cloning theorem, because no observer can actually verify both copies. And at that time, people were even thinking very radically that maybe in quantum gravity, you cannot have a global Hilbert space. It's only each observer will have its own Hilbert space. And it was not clear and it was never clearly, even now we don't have a very clear statement about what black hole complementarity means. It's something like a loose thing. And they claim it should be a consequence of these 4 principles, like unitarity of evaporation process, and some semi-classical geometry is valid, where you can do effective field theory and have equivalence principle at the horizon for the infalling observer. And then there are this so-called fundamental dogma that actually the number 4 is the equivalence principle. And the fundamental dogma is again that black hole is like some coal from the point of view of an external observer. And this black hole complementarity has been challenged from the quantum information theory perspective by AMPS, and earlier also by Mathur. But I think Mathur was not directly challenging the black hole complementarity itself. What he was challenging more was the idea that small corrections to Hawking radiation are sufficient to restore unitarity. But that is a different thing. But the original AMPS argument was targeted to, of course, black hole complementarity. And their argument was that if you look at a sufficiently old black hole, then you will have a certain amount of radiation emitted, and then whenever the new radiation comes out, it will start to purify. Basically, you will try to recover information of the initial state. So then it means that this early radiation and late radiation, this B and R, which is the late radiation is B and early radiation R, should have some kind of entanglement. That is, there should be a factor of R that is maximally entangled with B. Roughly speaking, there should be a factor of R which is maximally entangled with B. And B and A also should be maximally entangled if you believe in this, there is no drama at horizon, and that there is some effective field theory which validates Hawking's computations. And this is in tension with the strong subadditivity of entanglement entropy, which tells you that monogamy of entanglement is not possible. Again, this is a very superficial way of presenting it. So I just want to just sort of get along with it. The two possible resolutions of this way of doing things, and I take this terminology from Amartya Sen's idea of Nyaya and Niti. So you need two ways often to resolve something. One is as a matter of principle and also as a matter of practice, and both are somehow important. So as a matter of principle, of course, it has been argued firstly very brilliantly by Raju and Papadodimas that the Hilbert space cannot be actually factorized, and they were the first persons to point out that actually the interior, and the way to make it more precise is that the interior is encoded in a very state-dependent way in terms of at the boundary. But then I think Hayden and Pennington, I think, gave also a very nice way to understand the state dependence, but they've put it completely in the framework of subsystem quantum error correction. So I don't want to go into that. In my review, I think I have written an intersection on this. Then there is another way to do this, resolve this, and this mode of matter of practice is that in principle you cannot see the cloning, because in principle, if you have to see that indeed the cloning is happening, you have to be able to first factor out, you have to first locate the factor RB in R, which is maximally entangled in B. And this is exponentially, it should be exponentially complex in the entropy at the time when B is emitted. So that was the argument of Hayden and Harlow in 2013, that if you want to actually distill the factor that is maximally entangled, that would take exponentially large time. And then Tang and Preskill has made this argument more rigorous. And so there is two ways to look at it. And these two ways are not really disconnected from each other, because the fact that holographic reconstruction of black hole interior is state dependent and complex is something that has been discussed in many recent work by Engelhardt and Pennington, and also Susskind. They have brought in this new concept of Python lunch-like geometry of the interior that makes it possible. And so, but this is a lot of okay. So these are kind of the kind of very superficial review of this of the ways of black hole complementary as discussed in literature so far. So what I would actually do in this talk is to actually ask this question: how does black hole complementary principle can emerge from a microscopic description? Is there any toy model that shows that you can actually copy information twice, and what does it mean? And actually what we see is that in our toy models, that when we do that, actually the information is doubly copied into one case in something called a quantum trajectory, and the other it is in the von Neumann algebra. So I'll make this, I'll show in this toy models first. And then I will talk about whether there is there a microstate model from where within a local semi-classical description, but not necessarily global semi-classical description, complementarity can arise with an operationally smooth horizon and without paradoxes, of course. I'm not sure about whether there's still no paradoxes. I won't claim too much. but I mean, we are in the understanding process now, and of course, I'm not saying that we have been able to resolve completely all these issues, but I hope we have some interesting results. And but this question is in the same spirit as understanding the page curve from semi-classical black hole geometry. Okay, there is some debate and recently about whether this has been actually achieved or not, but what exactly, or whether the page curve is that what has been calculated. But anyway, but the main point is that the semi-classical black hole geometry seems to know in certain contexts about the Renai entropy of Hawking radiation and how much information it contains. So similarly, where we can get something like black hole complementarity with semi-classical approximation, but need not be a very global semi-classical approximation. It could be local in some patch, and that's the basic idea. Then the question is black, sorry? Yeah. Okay, you end of that. Oh, okay. So the question is whether black hole is just a pole or some special. After all, it is something special system or not. Yes. Okay.
Yeah, so the question is precisely that, one of the things I think we learned in the past few years is that some of these ideas don't have to do with black holes, right? That even in MTADS, for instance, you can see this fact that there's some information which is in the middle, you can get by measuring a local operator, but you can also get by measuring something at infinity. So it's true that some of these ideas were first thought of in
context of black
holes, but much simpler systems in gravity also demonstrate the same feature.
I agree with you actually. Yeah.
So will you focus explicitly on black holes, because if one wanted toy models, those would be simpler.
So actually, okay, maybe we can talk about it. No, but in principle, I agree with you. It doesn't have to do with specifically with black holes, but okay, that you need the special property of gravity that we need is something that I will call as a decoupling property in these toy models, and it's sort of quite evident in black hole-like phase, I would say. But okay, we can.
Yeah, in these simple systems, it emerges as a consequence of the constraints of gravity.
Yeah.
So, gravity has constraints which relate to things. I mean, the constraints on the object gravity. So something you measure somewhere is related. I mean, the simplest one is a Gauss law. You measure the energy at infinity, it's related to the So you see already there's some version. This is not, you need to do more. You see there's something you could measure the sun's mass by going into the sun, or you could measure it by just going around.
Yeah, but I'm not just talking of the mass, but
no,
yeah.
So you can get all information. So you can get everything, but about MTADS without ever talking of black holes by extending, just this kind of observation.
No, actually, the question is here whether suppose you start from an initial system, whether you can create two copies of the information which two different observers can access. So that's the question that I'm trying to resolve here. So it's a
but one sees that there are two operators that in quantum field theory would have been distinct operators that would have commuted, that in the theory of gravity are measuring the same object.
Okay, we will talk about it.
But isn't the last question a very specific one, and they should have an answer? The black hole is a special kind of hole.
It is a kind of hole. There's nothing different about hole. It's just that you should think of hole also in the same way. I mean,
no, but we don't think of hole in the same way, because hole, we know what the entropy of the hole is, right?
Sure.
I mean, you can talk about a localized hole, even though we are embedding it as lot of gravity, right? We describe hole with and without gravity in the same, right?
Because we neglect gravitation.
Fine.
So there's a sense.
So in the same sense, if I ask for the black hole quantum mechanics, right? For black hole thermodynamics, we can do it in the same way that we'll do for holes.
So can you somehow neglect these effects first?
Exactly. Yeah.
Okay, that's okay. Yeah. Okay, fine.
Precisely, that's the question.
After all,
yeah.
I mean, in string theory, we count the number of microstates for the black hole, and we found exactly over holes, right? I mean, if we think of it from the global perspective, that then nothing should have an entropy in that sense, right? There's no entanglement.
Entropy is a measure of number of regions, or number of microstates, right? That entropy we're measuring is not von Neumann entropy, that's just degeneracy.
That's the maximum von Neumann entropy that you can get out of the.
If you entangle it with an external system. But the idea that it's the entanglement entropy of the black hole with the environment, that's not supported. It's just the number of microstates.
That is true. But if you decouple gravity, for example, that will be a bound on the total entanglement you can get. That's like a pole, right? If the pole has certain number of microstates, then the entropy is the bound on what maximal entanglement you can get.
Yeah. In this case, this entropy would be the bound that you would get if you took the full ADS black hole and coupled it to something else.
I'm thinking of flat space, right?
Then we don't. Yeah. Okay. Then yeah. Okay. Then I don't know how you think of AFFOG as entanglement entropy. Is there but we can maybe this is going away.
I mean, that's the goal. Right? I mean, if we are able to decouple gravity and ask a question, right, then we can ask whether black hole and coal behaves in this way.
Yeah, okay. We could ask that question. Yeah, there are.
And I think that is a relevant question.
Yes. I mean, at least from a very far observer, I mean, who is like, for us, I think we are just seeing gravitational waves. We can think of them as waves on a flat space time. And think of it as, I think we can. Yeah. You go on. Okay, maybe okay, fine. Okay, so let me just start with two toy models, and then we see what you think about them. So let's okay, I will call the trumpet actually a JT gravity. So when we couple the classical system to a JT gravity, and that's what we want to do, you can think of the classical system as throwing some energy or some packets of energy inside the black hole. And what we see is the latter simply sucks away the energy of the classical system and typically drives it to the lowest energy equilibrium state. And this will explicitly see in a harmonic oscillator, for example. I will talk about the classical harmonic oscillator later, actually. First, I'll talk about the quantum case. And what we see is that two systems decouple in a trivial way because the other system has no energy, it is simply in the equilibrium state. And the black hole goes to some, without hairs, something that we know is a classical black hole. It's not fully true if the classical system also has an entropy. Then that is something we have seen later in some other higher dimensional black holes. But I'm not going to be focusing on that. First, the classical system is a simple system that has no entropy, like a harmonic oscillator. There's a twist to this simple story, even in the simplest case and even in the classical limit. But first, I will talk about the quantum case. So this whole thing will be very different in the quantum case, as you will see. And it will have a lot of interesting behavior. So what I will do here is that I will couple a qubit to the JT gravity. So a brief review of JT gravity is as follows, that so the only degree of freedom that the JT gravity have is something called the time reparameterization mode. And one way to put it very simply is as follows, that you take some standard geometry which has no ADM mass, and you do this time reparameterization, which you can extend in the bulk, and you get back something, something that is an ADM mass and a time-dependent ADM mass, M of u, which is simply the Schwarzian of the time reparameterization. And the Schwarzian has an SL2R symmetry, which is a symmetry of both these metrics. And actually, if you work out the details so the SL2R symmetry is something that takes a ingoing coordinate and outgoing coordinate and do an SL2R transformation on that, the same one. If you work out the details, you will see that this R is actually SL2R invariant. And M of u is also SL2R invariant. So it is SL2R invariant in a trivial way, this metric. So yeah, and this is the ADM mass of the black hole. Huh? Yes, I'm coming to that. So yeah, just hold on, yes. So, so the action of the JT gravity is this. Yeah, to answer your question, if you're in the absence of matter, the equation is simply half m dot is equal to 0. Yeah, so the mass is constant. Now, there is some bulk matter field which I need to couple a qubit with. And this bulk matter has satisfies Line-Gordon equation. And the only way you couple the qubit to this bulk matter is that you see the non-normalizable mode is expectation value of sigma x, where sigma x is a Pauli. Yeah, sorry. It was a typo. Thank you. Yes. So this is expectation value of the Pauli sigma x operator. And you see that automatically introduces some nonlinearity by hand, because expectation value of sigma x would be nonlinear in the input qubit. But this is part of the semi-classical approximation, that gravity only sees expectation values and not so the gravity here is classical. So we are working on the model we are actually working out the case where this bulk scalar is also quantized. And then this is very interesting to work out. For the scalar, not the dilaton. I think I made a very bad mistake. This should be small phi actually, not capital phi. Exactly. Thank you for pointing this out. So this was a very big error. So this is small phi, this is small phi, This is also small phi. Yeah. And that is dilaton. This is dilaton.
Phi is only in the first term.
Yeah. Sorry, thanks.
But sorry, I didn't understand this boundary condition. So you're saying this is the coupling between the qubit and the bulk qubit? This is just a postulated coupling. And
This is just a postulated coupling. So
what is the motivation for this form of the coupling or anything? Or,
yes,
so it will become clearer later? Or?
Yeah. So yeah, it's important to choose the coupling property, and in this example, and although it is yeah. So okay, so this is basically the way you couple it is that the source becomes some function of the qubit, right? Some expectation value on the qubit system, and that's the way you can couple. And
so you just chose sigma x.
Yeah. Yeah, for example, if you want to couple a holographic system to Maxwell equations, then you say that the expectation value of the bulk gauge field is simply the boundary Maxwell field, which has its own dynamics. So
this is the non-normalizable mode you're setting.
that's the non-normalizable mode. You are setting it to be
Yeah. So sigma. So the
expectation value of the sigma x as a source. I'm showing the full Hamiltonian, the full coupled equations here.
The sigma. So when you say it's a qubit, that's like independent of any space or anything.
It doesn't live in a space; it lives in time.
So
But boundaries anyway has only time.
So has only time. So
You know, the boundary source. You want a system where the source is much larger than the ADS. Otherwise.
Yeah. So here you're artificially taking the coupling to have some end scaling. Says that.
It's not a question of coupling. The degrees of freedom in the source have to be much larger because you want to treat the source as fixed. You know, when you say you have a boundary.
No. The source is dynamical. The source loses energy to the bulk. It will dump energy into the gravity system.
So there's a S qubit which will have there's an action for the
S qubit. Yeah.
S qubit.
So here you have written expectation value just because right now you want to be classical, or eventually you will make it just sigma x or no?
The qubit system would be completely quantum mechanical, but the gravity will only see the expectation value because the gravity is not quantized. It cannot see a quantum operator because the gravitational. So we are working where you can also have the bulk scalar to be quantized. If you quantize the bulk scalar, then you don't need to put an expectation value. Then you can simply evolve the whole system together and then take a partial trace.
So this system will treat purely classical, yes.
Yeah, the full gravitational system for now we are treating classical.
You're saying you want to turn a sigma x phi source, the sigma x phi term.
Yeah.
That's
I will write the Hamiltonian expression. The conserved energy I'll write soon. Yeah. So yeah, thanks for this question. So now so basically the equation of motion for the mass becomes this. This is something that has been derived by Madras and Zhang, and also it's in our paper. We derived it in a different way. With Lata and Alex, and we did. So there's this equation you can readily derive from this action, which is you can look it up in Madras and Zhang paper, and then
mass means some asymptotic value of the
mass is exactly this mass. It's exactly this mass. Yeah, and the small phi field lives in this metric.
The mass is no longer the Schwarzian. The mass is not the Schwarzian anymore, right?
The mass is still the Schwarzian. But so the equation will be Schwarzian. The time derivative of the Schwarzian is equal to this.
In another term, when you have a non-normalizable, then the mass is still given by du phi minus phi. It's still related to the dilaton in the usual way, but it's not the Schwarzian.
Here the dilaton is fixed. The boundary value of dilaton is fixed.
I mean,
if it is not fixed, then you get more terms.
The boundary is a dilaton isocircuit. That's what it's.
Yeah.
Yeah, but you can still look at du phi, the normal derivative, or dn phi, the normal derivative of phi. And the ABM Hamiltonian is always a normal derivative of phi. But I thought it reduces to the Schwarzian only when there's no non-normalized.
Yeah. So the actual derivative, so the actual Hamiltonian will be more complicated than this. So this actually you can write it as some h dot is equal to something which has a more conventional oj dot like term. And then so the actual Hamiltonian is changed by m minus delta O minus 1 O a sigma x.
Okay, there's one.
Yeah, you're right. I mean, that's the right way to do it. I didn't write it that way. Yeah.
UN is basically TUN, which is the stress tensor.
Yeah. Yeah. So if you write what you say is correct. So if you write TR mu and mu, this actually becomes simply, sorry, OJ dot, I think sigma x dot lambda. Yeah, and then the rest of the thing, actually, you can pull it to a redefinition of mass, but that will be a total derivative. Sorry?
One should be the normal, and the other should be along U.
Yeah, yeah.
So I don't know if n is a normal, it should be maybe T.
Yeah, I don't remember exactly. It is a normal to the fixed R hypothesis.
So you take T, one component is a normal, one is along U.
Yeah, you're right. I think you're right. This is T. Yeah, you're right. Yeah, this is, I wrote it wrongly here. Yeah, this TU, yeah, mu. Yeah. Yeah, yeah. But anyway, so what happens if you do that, then this will become a mass would be actually a plus some corrections, a total derivative, and then you get the conventional term. But this is, but I wrote it in this way because it's more useful for us. Okay, so the qubit Hamiltonian, like the qubit now has this Schrodinger equation, which is like this. So it sees the, so basically it sources the operator in the bulk, and then it back reacts on the qubit. So you have to solve this whole system consistently. So you have to solve the mass equation, and you need the mass equation because you have to solve the Klein-Gordon equation for this small phi in this background. And then you have to extract the O from the fall off behavior. And finally, you can also, so it's, you have to solve the whole system in a self-consistent way. Now, Schrodinger equation, what I can do, I can also take, instead of a pure state, I can also take a mixed state, and I put it on a Bloch sphere. And because this density matrix has only positive eigenvalues, you then get this restriction on U1 square plus U2 square plus U3 square, positive eigenvalues less than 1 and between 0 and 1. So that this restriction comes from there. So you have this, this is the density matrix, and it has the following evolution equations. So essentially you have to solve this equation, these three equations, the Klein-Gordon equation and the mass equation simultaneously. Okay. So now if you, now there is a total conserved energy of the system, which is the energy of the qubit, the interaction term, the ADM mass, okay, forget this factor of half, it's a little bit unfortunate. And then there is this other thing also, which is the, actually, sorry. Yeah, so these and these together are the interaction terms, actually.
So the Klein-Gordon equation on the full back reacted background.
Yeah.
With the M.
There's a back reaction. No.
He's taking M of R.
M of it, it's still pure ADS, but it's time reparameterized. It's large difference.
So it's a Klein-Gordon equation
in that M of U background. Yeah. So you need that. Yeah.
I'm just because I don't know so little about this. I thought the standard way to do this was you fix the background to be ADS, and you just allow the boundary to fluctuate.
You can do it that way too, and that you can also do. But then you have to map it back to the real physical background by doing this time reparameterization.
Or you just, I mean, it's the same equation. Right?
No, it's different because this equation, if you can either write it. So I actually gave a talk in TFR just on this last time, like 2 years back or something, and so I actually explained all that. But yeah, it's a little bit convoluted. You can do it that way, but I don't want to get into all those, like going from one picture to another picture. And but you're right. I mean, effectively, you can also do it like that. Yeah.
And that would make this a little cleaner, right? Because it would make there would be no back reaction on the geometry. The scalar would be propagating.
Well, there is a back reaction in some sense that you are, because the time reparameterization is driven by the source, right? The time reparameterization changes, and not by simply an SL2R.
The Hamiltonian you wrote now, it's always coupling to sigma z plus sigma x. Here, why did it O sigma x and O sigma z?
Maybe this, okay, sorry, I think this term maybe should not be there. Yeah, I think, okay, this is a mistake. I think this term also is not there. I think, yeah, there are two terms. This is the qubit Hamiltonian, this is the actual mass, and this is the interaction.
Why O expectation of sigma x as opposed to expectation of sigma? I mean, why not? Why take an expectation?
Because this is a scale, this is not a quantum operator. It's a classical thing that is conserved by the dynamics.
But the quantum operator is also conserved, right?
Well, we have a semi-classical evolution here, so it's we can only do it this way. because there is no, because the whole system is, yeah, this is the artifact of the semi-classical description, that you do not have a expectation value. That you don't have, you have to have an expectation value.
I thought you have a scalar field which is fully quantum. And then there's a boundary.
No, scalar field is not fully, scalar field is classical. The qubit is quantum, but the scalar field is classical. So therefore, O has no expectation value. O is, I write O as.
Why you are treating it as classical? I mean, can't you think of the quantum field? Scalar field?
Oh, just for simplicity. But we are now working on the version which is also quantum. It becomes more complex. I think this already is quite complex to simulate. But yeah, you're right. I mean, in principle, you should also treat it as a, and in fact, if you want to treat Hawking radiation, that's the best thing to do.
Yeah, because if you are coupling it to a qubit, I mean, the only consistent way is to make the whole thing quantum, right?
In a way, yes. In a way, yes, but this is how we, but otherwise, how would you do semi-classical gravity? Like when you do all this off-page curve computations also, you treat,
when you do in quantum mechanics, you treat the electron as quantum mechanical, but the radiation field as
classical, yes.
The explanation for that is the radiation field has a lot of degrees of freedom, so it doesn't fluctuate. You know, there's a reason. I mean, you could, for instance, treat the source as classical, and the bulk field, and the justification for that would be the source is so much heavier that you just fix it.
Well, in a way, this is the same thing here. The black hole is supposed to be like, if you think in this way, it's like XYK quantum dot. It has many degrees of freedom, and qubit has only one.
It's the opposite in this case, right? So
no.
So you say that the black hole is classical.
Yeah. I mean, it's not opposite.
So I think it's exactly like.
Yeah, you can think of it like a qubit coupled to SYK quantum dot.
Like a back reaction, but thinking of the expectation value of sigma x, right? I mean, otherwise, I would have thought that there should be no back. I mean, you should ignore the back reaction altogether, right? With sigma, the idea is that you want to study the fluctuation of sigma x in this background.
No. The idea is to see how the double copy of information is happening. So then you have to consider back. It's like in the page curve computation, you allow the back reaction, right? Otherwise, the black hole will not evaporate, and you don't see the quantum extremal surface emerging and new kind of.
Yeah, maybe what bothering me is the boundary condition you put in the scalar field. You put a boundary condition which is that the limit of O is a non-normalizable. That boundary condition is usually put in the other limit, right? Where the source is classical. Here the source is a qubit, and you're forcing this classical guy, this classical source. Make a boundary condition.
Source is just expectation value.
But that is what's bothering me. That the source, you have a quantum object, it's coupled to a classical system, and then you put a
but that's but this is something that you also do, like
Psi bar gamma mu psi or something like you can take its expectation value, current coupling to the.
So now you want to set the classical radiation field to have a boundary value which is set by the classical expectation value of the
Yeah.
So the classical radiation field is not bigger, it takes the boundary value, it doesn't take boundary values from something that's what I'm worried about.
well, people do it for superconducting qubit also. Like you take something, you couple to some radiation first order.
First order change in the just
well, I'm sticking to all orders, but yeah, it's only in the in the GN, yeah, G Newton. It's a G Newton is exactly. It's because G Newton inverse corrections are large N corrections. So you have one qubit coupled to, and this is what in the full talk I will only talk about a small system coupled to a large black hole system, black hole like system, but never other way, because so in that way you're right. Then I cannot treat, it's not consistent to treat the gravity also as classical if they're of the same order of degrees of freedom.
Yeah, no, the only thing that's bothering me maybe is that the qubit is 1 degree of freedom, whereas expectation of sigma x can change as you go up and down. I mean, expectation of sigma x is not time independent. As it changes, it drives the whole scalar field has to change according to the value that this qubit is.
Yeah. These are to follow these equations basically.
Yeah. It is forced to change. So the whole scale.
By a tiny bit, by a small bit. Right?
No, big amount. No? Because if you change sigma x to go from 0 to 1, so then the whole scalar field, which was first had a non-normalizable mode, now it has to completely kill that. It has to go down to 0.
No. So see, what happens is as follows. If you okay here, okay. So what happens is as follows. So you see that black hole will gain some mass from the qubit, but a small amount of mass. It's a small change, not a big change. Let me go on. Let me tell you how the solution looks like, and I can explain that. So here you're artificially actually blowing up lambda to be large just to make it, some effect that is visible. But in principle, lambda is a small quantity, as Rajesh was also saying. And what happens is the black hole will simply suck away energy from the qubit, and it will only have a small increase in mass. You see the total energy that I plot in maroon here, that is conserved. The interaction energy has some wiggling and it goes to 0, and the energy of the qubit goes down. Okay, the energy of the qubit kind of goes down.
Those are the 3 different terms.
Yeah, those are the 3 different terms, and E total is the total energy, which is conserved.
So the top term is the mass term.
Yes.
The one that's increasing is the mass term.
Yes.
The one that's more or less remaining flat, the wiggle and then flatten out.
Yeah. So this E spin is the energy of the qubit, which is H0 sigma z term. This one, of course, goes down because the qubit is driven to the ground state. So here we will see there is a partial double copy of information. I'll show you how. So here information is lost only partially, but for the quantum harmonic oscillator, information will not be lost at all. And this is surprising, but yeah. Okay, so what happens is that this is the sigma x expectation value term, which has O sigma x. This is the yellow term, so it goes to 0 at the end of the day. I'm solving the full quantum system actually. So it's not the quantum system I'm treating exactly.
What is LADS by L Planck?
Well, that is all in the M, right? It's n square. Large n. This is large n. So the way you should think about it is this is some sort of a graph that is magnificently blown out of proportion, where these changes should be rather small, and this should be also small. But I've blown everything up there. So the point is that the mass, the change in the mass of the black hole should be very small compared to the actual or initial mass. No.
Because there should be a coupling constant somewhere there. In the equations.
Yeah, lambda has to have some scaling over n. Yeah, 1 over n lex. Oh.
In the gravity, because the n itself comes with a factor of g.
Yeah.
The back reaction of inserting 1 unit of EDS energy on is very small. L Planck is much smaller than LADS. So there should be also LADS by L Planck should appear somewhere. And I'm worried why this effect is so big. Like if one qubit changes, why does the mass change?
Mass is changing by 1 over n square.
Yeah.
I mean, compared to 1 over n square compared to the.
Where is the n square in the equation?
Well, that's suppressed.
It's there.
Yes.
It's one. I mean, it's order 1 if you compare the leading one as 1 over g.
I don't understand. But then, so you're saying actually there should be a n divided by a huge parameter, which is like n squared. Shouldn't it also appear in the
Well, this m is something which is actually very small, right? Because this m is going from 0 to.
No, m goes from actually m will go from some non-trivial value, but the change in m will be small compared to the original m.
Change in m is
Small.
So this is, if you wish, the delta m.
Delta m is small compared to the original mass.
So you have said G Newton equal to 1, that's why it's hard to see.
Hard to see what is small, what is. That's unfortunate, but.
Because it's G Newton equal to 1 and also said LADS.
No.
Maybe you said LADS equal to 1 or said G Newton.
LADS will never appear physically in any quantity that you measure, right?
I think it's just fixed coupling probably, right? This
Yeah.
coupling constant of order.
Infinity is a
and LADS I think are to the same order, no?
So G Newton and LADS are the same. Yeah, that's what is worrying. It sounds like the regime
have the same order.
is equal to L.
So we are taking the large n approximation. So LADS completely disappears. Actually, it never appears in any physical quantity, any holography, because you absorb it in m. right? The only way it appears is capital N, which is LADS by this related to L Planck versus LADS.
It appears in the, you see when you wrote the metric
Yeah.
previously, that metric comes with a factor of 1 over n.
Yes.
So if you inserted one unit of energy in the limit where L Planck was 1 unit of ADS energy in the limit where L Planck was much smaller than LADS, there would be no back reaction.
Well, okay, so all the LADS dependence is in O and M, where have their factors of n, and they have the same factor of n square here, because it's LADS by, okay, there's also some bulk dilaton in the business.
The scalar field.
No, it has, because, okay, that depends. So here in the action, I didn't write 1 over h pi g here, and this 1 over h pi g should multiply the whole thing, actually. This whole, both this part and this part.
It should only multiply the phi into r plus 2, it should not multiply the del phi square. That's a canonical nominalism. The second part is not divided by 1 over h pi g. There's a relative factor.
I mean, you can just absorb it, right?
But that's the field.
Yeah. You can absorb.
Because it has a matter plus gravity system. Coming from some supergravity or something, you would get it.
Yeah, yeah.
Normalized.
So I think what Shuvra's worry is that what is the scaling of lambda should be like, basically.
So lambda is small principally in this
Yes.
language, right?
Yeah, in this language, lambda is. Yeah.
Independent of n, it's some small number.
Yeah.
Yeah, some small number.
Yeah. And the main point is that you're interested only in the delta M, which is small. I mean, so everything here is very small in 1 over n. Nothing is of order 1 or something. Okay, maybe, yeah.
One thing will show the equations actually which you solve to get these.
This one's.
Yeah, maybe one side.
Yeah.
So let's say there was, maybe you're right, there is. So if there was a factor of 1 over n squared, then we would have m dot is extremely small. Not only is it suppressed by lambda, it's also suppressed by a factor of n squared. Because the way you defined m dot is, I think, in the ADS units as the subleading term in the metric. So if there was an additional factor of n squared here, that would be the
but I can still solve it exactly, no? What's the
you
difference?
can solve it exactly, but
Yeah.
it will make a difference in the
It will simply tell you the small delta M is small compared to M.
I mean, I think lambda is small because it has 1 over n square, right?
Yeah.
Because G Newton is absorbed inside lambda.
Yes.
But it didn't have G Newton, so.
But then we shouldn't have the top part, which is the limit of the scalar field is given by some 1 over n square. Usually you set the scalar field to be go to a boundary value, which is just fixed. There's no n squared in that boundary value.
But it could. I mean, that's what he's doing. This lambda is technically small.
Small.
1 over n squared.
Small effect on the.
It's a small perturbation on. I mean, you don't normally do it, but yeah, you can do it.
Yeah. Exactly. Yeah. Normally, this is not what people do. Yeah. Normally, you set order 1.
The back reaction, which is comparable to your original. Here, it's not a back reaction, which is comparable to your original geometry. Okay, you have to probably argue that where the quantum effects. I mean, why is it a controlled approximation?
Yeah.
Another factor of n, even if lambda was.
Well, yeah, it may not be completely controlled. I can agree with that. May not be fully controlled because, yeah, it is. But
in the last equation, addition to lambda, or you could put n squared in the definition of n where you define it with respect to the metric.
yeah.
So somewhere there has to be n, 1 more n, even if you take lambda to be 1 more.
Yeah, but I think the spirit you should be taken that is that it's a small effect and all these changes are very small, but they are still exact solutions to this system.
Yeah,
and
normally you don't do it that way.
Normally
there
don't do
are quantum fluctuations of the same order.
Same order.
So
Yeah.
you would have to consider 1 loop gravitons or
Yeah.
1 loop.
Exactly.
Also.
But here I'm not doing that, which is that's where it breaks, the controlled approximation if you want. Yeah.
Well, I think I mean, if there is a dynamics of sigma x, right? So you could use that to make the fluctuation small, isn't it? I mean, when you say, it can be controlled by controlling the dynamics of sigma x, right?
Yes. Well, we're controlling H0, maybe this.
Controlling the dynamics of sigma x.
That you don't let sigma x fluctuate very much.
You could couple it to some huge qubit chain of which the gravity only couples to the last qubit, and most of the dynamics is coupled by the rest of the chain.
Yeah.
So that's why it behaves approximately classically. But then it would of course be other approximation, and he wants the approximation.
Yeah, it's not very rapid. It has only a single qubit.
Okay, maybe I can go ahead. Okay, so what happens is that, okay, so, yeah, I mean, okay, so this is a question whether, okay, we have to discuss it further, whether this is a controlled approximation. But for the moment, just think of it like a toy model, and just where you ignore graviton loops and all this. And yeah, so, and then you get all this interesting dynamics where you see this decoupling. So what happens is that the U1 and U2 goes to 0. So basically you're losing information because U1 and U2 goes to 0, and U3 doesn't go to 0, it goes to some negative number. So what is happening is that you might think there is nothing, sorry?
I have a question. Like for the qubit case, is your qubit system sourced by the expectation value of the sigma x, because it forms a boundary value of the graviton system, right? So usually what forms the graviton boundary value, I mean the boundary value of the bulk system sources the conformal field theory or the boundary system, right? So is that the case here?
Yeah, it's just simply sourcing by the scalar field, yes. Yeah, the qubit is sourcing the scalar field. That's how the coupling is operating.
So the expectation value of the qubit is sourcing the qubit system?
Yeah. The expectation value of the bulk operator sources the qubit system in return. So that comes from here because this term tells you that otherwise the qubit has its own Hamiltonian, which is simply it's in a magnetic field or something, H0. And then this is what back reacts back on the qubit. Okay?
I mean, I'm not sure where I can see the expectation value.
Expectation value? What? So here is the expectation value. So
see, the sigma x expectation value is something which sources the bulk system, right?
That I already wrote in this equation. Sorry.
Yeah.
Here,
yeah.
I wrote this.
Yeah. Yeah. So here, as you can see, this lambda sigma x is the boundary value of the bulk field.
That's exactly.
So that means that this is the thing that should source the boundary field theory or whatever.
Yeah, that's exactly what I said. Yes. Yes, I agree. Yeah. Yeah. Okay. So anyway, so this is what is happening. So we have this ring down, and the way so now let us think of it as quantum channel, like an input qubit and output. What is happening? So the input is this density matrix with this bound that is built into it, because of these are the eigenvalues will be probabilities, and the output qubit is this. So you see it's a nonlinear quantum channel because it depends nonlinearly on the inputs, but interesting thing is that the purity remains the same. The purity is simply trace rho square, that doesn't change. And that you can already see that U1 square plus U2 square plus U3 square is invariant, because after all, basically it's a state dependent unitary evolution, because the evolution is unitary, but it is conditioned by the state itself, because expectation value of O comes from solving the system. So it's in a way, it's a nonlinear quantum mechanics map. And so this is something that has been discussed also in the context of superconducting qubits in literature, superconducting qubits coupled to cavities. And so what is but there are some big surprises here, which is something that I want to point out. So although it looks like nothing special is happening, that after all the qubit is driven to the ground state where it has minimum energy, and it is subjected to the fact that the purity is conserved. So the eigenvalues of the input and output are the same of the density matrix, and purity of both input and output are same, which means that the von Neumann entropy and Renai entropies do not change. So here is a very interesting quantum channel. I think I showed it to some of my colleagues and they were really surprised that this is one example where information is lost, but the von Neumann entropy and nothing is changing. because the eigenvalues of both input and output are the same density matrix. But the basis in which it is diagonalized, that is lost. So now, no, U1, U2, U3 are real, of course, yeah. They cannot be complex. So, so what is happening here is something even more interesting, is that the purity and U3, these are the two numbers that you can recover from here. You can recover U3 so if you look at how much energy has been lost in the qubit, that measures U3, and the purity would be measured by the final value of the energy. So I simply trace rho square. Yeah. And it is bounded from half to 1. Sorry. So, that's a good question, actually. I have not thought about it.
Because it seems to me that you just have a magnetic field, and whatever you do, after a while, you go to this point along the magnetic field, and then you would always get the same answer.
Yeah, it's a good question. So what would be the output state? Yeah, that's a very nice question. Very nice question. I have to, yeah, no, that's a good question. I have to think about it. Yeah. What happens if we have to?
What they ask is, this are not understood. Why would they be square root of 1 square? Whatever you're coupling, you just have to.
Exactly.
We just make it point wrong direction. You can make it down. Now, that's not what is happening. It's becoming half of identity. That's not. That you have just below some of the. I should say, why is this normalized?
Well, the probability is the eigenvalues of density matrix has to be positive and between 0 and 1.
I see. So any coefficient you had for sigma 3 would go. Let's say I give you a different coefficient for sigma 3.
No, this is simply an arbitrary input. I tell you what's the output. How is the quantum channel looks like.
So I'm just trying to understand. This Noga's thing, let's say you turned off magnetic field.
Then there is no preferred final, because here everything goes to sigma 3. There is no preferred direction. That's what he's saying.
Yeah, but the question is the coefficient that's appearing in front.
Probably take epsilon magnetic field and the limit.
But yeah, but then why sigma 3? Why not any other?
No, that's why you break it.
Break it by epsilon.
And then
switching it off. Yeah, that also can.
You can't even obey the Lindblad equation. So
well, I'm solving it completely. Yeah.
No, it's not unitary. That is completely breaking the Lindblad. You would never get this by coupling the qubit to a unitary system and solving the whole system.
It is unitary because these equations are unitary, but not unitary in the traditional sense, because it's a nonlinear quantum. This is what people, the quantum information community now call nonlinear quantum maps. It's not like saying that quantum mechanics is modified. It's because of the semi-classical approximation. What is happening is this O is being conditioned by the qubit itself. It's a state-dependent unitary in a way.
If you took a big bar, like, and you coupled it, but the whole system was unitary, there would be a Lindblad equation which would have to solve.
Yeah, and that's what we are doing. And we also don't have to do that. You can also try to, if you can solve it exactly, you solve it and then take the trace.
This will not come from the result of any Lindblad equation. This is genuinely not.
Hopefully, yeah.
No Lindblad equation.
Yeah, I agree with you. The Lindblad equation is also linear. It's not nonlinear. So yeah. So yeah. So this is what you get, and then the point is that if you look at the black hole ring down, what is happening is that there is some decay exponent, there's a frequency, there is a phase, and there is an amplitude. There are 4 things. So it turns out that of these 4 things, 2 are pretty independent and essentially given by the amplitude and frequency are pretty independent, and they are set by frequency, essentially the Rabi frequency. But what I want to tell you is that JT gravity has no quasi-normal mode. So this ring down is not a feature of linearized perturbations. And if you do linearized perturbations, you don't see this ring down at all. So you have to actually go to second order to see something like this in perturbation theory. So actually this is... Huh?
The output value of a node.
Mhm.
Identity minus sigma 3.
That's because you lowered the energy and the magnetic field is in the z direction. 3.
Because OL acting like a magnetic field of
Oh, switches off. So once it switches off, there is no preferred direction. But maybe it remembers. So maybe it goes through in the x direction. I don't know. That could be the answer to the last question. Because
the strong magnetic field, why doesn't it point along sigma? If the limit to h0 is infinity, surely they should point along sigma.
that's what is happening, no? What do you mean? Sorry. What do you mean? Sorry.
Let's say I had a very strong magnetic field.
Uh-huh.
Yeah, like
It is
h0.
pointing.
It is
Even not, you don't need
Yeah,
a
very strong.
any magnetic field, he's saying. Because the output is sigma 3.
Is
The
in
output is 1 minus sigma 3 and 1 plus sigma 3. It's not just
what? No. This is the final density matrix. This is the final density matrix.
I know, but
So it is pointing the sigma 3 direction, right? So if you diagonalize it, it is in the diagonal in the z basis.
I know, but can't I make like up spins like completely preferred? This is not, I mean, there's some ratio of up and down.
Well, you have to preserve the purity. So within the constraint that the purity is conserved, this is the lowest energy state.
Why can't I make it 1, 0? I could make it like
Then you don't preserve the purity. Then you're making it more pure. Then suppose you start with a mixed density matrix, you cannot make it pure density matrix.
Well, in this nonlinear evolution, you probably can. Right?
No. I mean, that is also not, it's not anything goes.
He's saying it's still unitary, preserves rho square and
No,
preserves
Yeah,
eigenvalues.
preserves the eigenvalue. It's almost unitary.
He's saying that those coupled equations that you wrote, even though they're nonlinear,
Yeah.
they preserve the norm of the rho. I mean, they preserve the eigenvalues.
Eigenvalues.
That's what he's claiming. Right?
Yeah.
You're claiming that those
Yeah, that's what-
coupled equations that you have. Yeah.
You can easily check it, right? U1 dot plus. Yeah.
Look at the time evolution, it preserves the eigenvalues.
You know use that. Just take you because it.
Yeah. Effectively something like that. Yeah. Still unitary, but non-linear thing that depends. It is, as he said, a state dependent. Unitary.
Yeah.
Then we change rho phase balance. Oh, I see.
Yeah. So what is non-trivial here when you're coupling to the black hole is that there is automatic decoupling, which doesn't happen for superconducting qubits and all these other things when they're coupled to cavities. And as I said, the purity and U3 are kind of encoded. So if you take all possible U1, U2, U3 in the Bloch sphere, they map to something like a two-dimensional surface where you find the decay rate and the phase. The amplitude is independent. The frequency is the Rabi frequency. And this decay rate actually encodes the purity. So essentially the story is that information of purity are encoded both in the output state and the black hole ring down, and information is partly copied twice. Okay, so this is what I want to say that. So if you look at the information in this original qubit, you're losing the basis in which is diagonalized, but you're retaining the information of the eigenvalues. And that you can recover independently in two different ways. One is by looking at the output qubit and measuring it, and the other is by measuring the black hole ring down. And these two are independent measurements, because once they decouple, they become independent systems again. And you can recover it in two independent ways.
So you say, okay, from the output qubit, okay, you can recover U1, U2. I mean, you can
Recover the purity.
The purity, okay. And then what do you say from the black hole? How do you recover?
The black hole you recover by looking at the decay rate of this and the phase of the ring down. Of course, the phase you have to define with respect to some arbitrary reference time. You set some normal reference time and you do the Fourier transform, and that defines the phase for you, or to try to fit to some particular frequency. So, so here the data one has to take very high quality data and wants to look at very late time to get a very. Otherwise, you won't get very. So the reason that these are like statistical fluctuations. So this is only very data which is quite preliminary. But of course, what we are sure that this decay rate is encoded in the purity, and the phi will capture some the original U3, the original component here. So if you know, so basically you can know the original energy of the qubit from the ring down. The another way to put it is as follows: you take randomly all possible initial states on the block sphere and try to see where they map to in this plane. And you find they span a two-dimensional surface. So it means that you retain, you measure you retain out of this three-dimensional information, you retain two-dimensional part. So that is the original U3 and the purity. What you don't know is U1 by U2, the ratio of U1 and U2 in theory. And like if you look at superconducting qubit literature, there are some examples of such nonlinear maps. But the unique thing is the decoupling, which is spontaneous decoupling is only possible if you couple to a black hole. But what is surprised is that purity doesn't change and the quantum entropy doesn't change, although you're losing information. So I think this is something interesting, and the fact that you are partly copying the information twice is also very interesting. Yeah. Yeah. That doesn't happen if you couple to a random cavity, because that will never disentangle or decouple from it.
But here that's probably because like you're just letting things fall in. You're not letting the output be.
In a way, yes. In a way, yes, but yes and no.
In this case, it's all died down.
Yeah, that's why you are in down.
But actually, you also take into account the fact that the laptop also emits.
Yes. Yeah.
And like it will keep that.
Well, if the Hawking radiation, yeah, so that's what we are trying to do now. What we are doing is quantizing the field, the bulk scalar field, and that will have the Hawking radiation and seeing what happens with that. But I don't think the features will change so much, because the fact that this is tied to the fact that we are taking the JT gravity in a semi-classical way. So I don't think that will change this result so much. But yeah, you have to take into account sigma x fluctuations. It's not, but
I mean, we also talked a lot about state dependence. This is bothering me in some very significant.
But it's not your kind of state dependence. Yeah, it's a more mundane state dependence.
This euro is like is really violating like as Loga is saying, right? Like it seems to be very seriously violating.
No, this is an artifact of the semi-classical approximation. It is something very well known. It's not like something that, it's not like a changing the rules of quantum mechanics. It's simply an artifact of the semi-classical approximation.
No, it's not an artifact. It's doing something which it's not like this. You will get this as an approximation to any quantum mechanical system. Because it's really nonlinear. It's like doing something very nonlinear.
But you do that, like you do some Hartree fork or something in quantum mechanics. I think you do something roughly analogous. I think
you some energy levels, but
well, it's also qubit. This is not something that is. This is not a very big system.
Maybe if you want, if you entangle this qubit with something else and you start doing non.
I'll talk about it. Yeah, I'll talk about it. Yeah, that will create a lot of interesting stuff. I will talk about it. It will create very interesting nonlinear protocols, and I will talk about it. Just then ask me the question again. Okay, maybe I can go ahead and couple a harmonic. But this is really.
Why do you insist that you want to speak now? Because semi-classical things are not very.
Harmonic oscillator. Largest. Yeah, that's exactly what I'm doing now. Largest is similar. So what I will do is a quantum harmonic oscillator. So here it's very interesting. So here this will be a very similar analogous system, where here now what I couple, the black hole couples to here it is lambda x expectation value. So instead of sigma x, it will be the phi non-normalizable mode will be equal to lambda x. Okay, so that's the only change, the expectation value of x, and this is the equation that you get instead of the earlier equation, and this is a Schrodinger equation that you need to solve. And a plus a dagger by root 2 is nothing but the quantum x operator. I simply have written in terms of a and a dagger. And this is a conserved mass of the system. Okay, so this is this rough small change. So I'll tell you how to solve the system. So first of all, I don't know whether you've seen this. You have seen, I think, this object, exponent minus this is nothing but a coherent state. But this is actually also analog of the excited coherent state, which is where you take the harmonic, the Hermite polynomials, and you shift it by the same xpt. And then you define this phase factor, which is the action plus omega t n plus half. Okay, so this is some definitions only. And so this will help us to solve the system, this Schrodinger equation that we are talking about. So the way you solve it is that you first take this as an input state, an arbitrary pure state. You can also do it for a mixed state, but to simplify the discussion, I only talk about pure state here. The time dependent state is like this, where this psi 0t is simply this thing, is a coherent state, and psi 1t is the first excited state. So 0 and 1 are the ground state and the first excited state. And this goes to a superposition of all Fock space bases, and this is all soft Fock space basis, but this is the first excited state, first excited coherent state, and this is the original coherent state. And then you have these arbitrary phase factors, not arbitrary, F0, F1, which is basically this. And for this to be a solution of the equation that we wrote down here, for this to be a solution of this equation, xp has to solve this equation, and p has to be h dot. And the initial conditions are this, actually. Okay, sorry. I'm sorry. I don't think this had the right initial. No, okay, I have to. Okay, so I take back. I think the initial condition can be simply obtained from here. I'm sorry. Maybe this is not the correct thing which I wrote. Yeah. Sorry? Yeah, it's a harmonic oscillator. Yeah.
And where did the equations come from? The harmonic oscillator coupled to the black hole.
The O couples to X.
O couples to X.
Yeah. And this is a way to solve the equations.
And then Hamilton was commissioned that this side of this is a
commission. Yeah, this is simply a Schrodinger equation. Yeah, it's state dependent. In the same sense that the qubit was.
Why is it state dependent? This is a commission.
Because of O.
Because O is usually
that's self-consistent.
O is going to make a function of psi.
Self-consistently, yes.
O function.
Okay, so now comes a very interesting, this is the most, what will happen here is far more interesting. Well, this side is not so super different. So here you have a constant energy, the maroon line, the mass of the black hole increases, the mass of the harmonic oscillator decreases, but it doesn't go to the vacuum value actually. It doesn't go to the vacuum. It doesn't suck up all the energy. In fact, the amount of energy, because the energy sucking itself is like a measurement. It measures something of the initial state, as you will see, and then the interaction energy goes to 0. The important reason why this happens is that the expectation value of x and p both go to 0, and they ring down, and there's a decoupling, and the quantum harmonic oscillator decouples from the JT gravity. No, expectation values, I mean, in a quantum harmonic, in the ground state of the is delta x delta p, not expectation value of x, expectation. I'll tell you, wait. Yeah, okay, you can do, yeah, if you so I'll tell you, just hold on. It's not 0, of course.
Yeah. So here, it's a kind of systems. If you further, is it stable?
Is stable, yeah, it's stable. You can see the stability through the ring down, but this is stable. I mean, if you just do the linear perturbation, you don't see anything. You have to go to nonlinear order to see anything, because at the linear level there is no quasi-normal movement.
Schrodinger equation here is going to get some nonlinear Schrodinger.
Yes.
Because there's very stable.
Yeah.
So
it's not nonlinear Schrodinger equation in the usual sense. Like it's not a modification of quantum mechanics, but yeah.
Like the science also.
Yeah.
It is a modification of quantum.
No, it is just semi-classical approximation.
Oh, you're putting a Hamiltonian which depends on the state. You can't use it as a Schrodinger equation.
Yeah, but it's, as I said, a Hartree-Fock approximation, you do that, right? And
it's an energy level. How do
no,
I know
you write a Schrodinger equation also too, right? I mean, you try in the mean field, you put the average energy, you write the Schrodinger equation with the Coulomb energy being coming from the side dagger side. Yeah. And that's how you write the solve Hartree-Fock. You have a large collection of electrons. You want to look at one in the presence of the mean field. So it's like a mean field approximation.
Yes.
I think if you use the action equation with quantum stress tensor.
Yeah, exactly.
You start with expectation value of operator as a reference.
Yeah,
Because if we solve it.
That's true. That's exactly. That's true. I mean, it's true. You get this kind of a structure, and so I agree that yeah. Okay, but I was asking that, like whether there's a stability of
it is stable. It is stable. We perturbed it, and I mean, there's this. You can do perturbation theory, but it's a non-linear perturbation. You have to go to at least second order to see. But it is, yeah. But it is. But I mean, the stability is kind of apparent. No, there is some arrow of time in the sense that the black hole mass always increases; it never decreases, and from the initial value, it's not monotonic, but.
how sensitive is it?
No, there is no chaos here. There is no. There is pseudo randomness in many ways, but okay, not even. I will comment on it. Just hold on. So anyway. So here you see this thing, and then we have the decoupling. So let me now explain what is the final input state and output state. If this is the input state, the output state is actually a quantum trajectory. So what is the solution of? It is solution of the decoupled Schrodinger equation, which is simply this. A dagger plus A plus half without this term. But it is a non-trivial solution. It's not an eigenstate of the energy. It's a quantum trajectory. And this quantum trajectory is of the following way. It's again psi0 t, psi1 t, and with the same definition f0, f1. But now you see xp is a solution of the decoupled equations. And it is capital A, capital B. But this capital A and capital B is fully determined by the initial qubit. And the way it is done is that your expectation value of xt will be 0, and this is satisfied provided A is this thing and B is this thing. So essentially the point is that although expectation value of x goes to 0, the state is a very non-trivial state. It's on a quantum trajectory. Yeah.
This is not an eigenstate, right?
This is an eigenstate. No, this is not an eigenstate of Hamiltonian.
But you had an energy which was flat. Right?
Yes, the expectation
So
of the. It's the expectation goes to is flat. It's not an eigen. Expectation value is still constant. That can happen, right? Expectation value can be a constant, although it's not an eigenstate.
No, but you said that the time evolution after a certain point is just given by the this thing.
Yes, but for example, when you have a coherent state, the expectation value of energy is still constant. Yeah. And so this is an interesting thing because the output is not really a fixed state. It's not a eigenstate. It's a quantum trajectory. And in this quantum trajectory, you can completely decode the initial qubit. Because to get this quantum trajectory, all that you need is value of xpt, which is this capital A, capital B, and that is given by this theta and phi. Now, the interesting thing is also that the amplitude and phase of the black hole ring down also carries complete information of the qubit. So if you look at the input initial energy, so the amplitude of the ring down would carry information of the initial energy, and the initial x by p will be encoded in the phase. So here, what is happening is that the output quantum trajectory of quantum harmonic oscillator maintains coherence after decoupling and is determined completely by the initial qubit. And also the output semi-classical ring down will carry complete information of the initial qubit of the two angles of the Bloch sphere. So this is so far a pure state. If you do a mixed state, then the decay exponent would be encoded in the purity. The important thing is that from both we can recover the initial qubit fully and independently. Information is copied twice. So this is an example where you can recover the information in two different ways and independently from the initial thing. So I skip the classical limit. In the classical limit, okay, I just simply say that in the classical limit, what happens is that instead of the energy really goes to 0. Here the energy doesn't go to 0. Here it goes to some particular value, which will be set by capital A, capital B. And this capital N and capital B will determine what is the final value of energy. Yeah, and to answer Rajesh's question, yeah.
The problem could be the interpretation, right? Imagine that you have a regular Schrodinger equation, right, which is perfectly linear. Now you want to do, you can lift it to a field theory, right? Schrodinger field theory, where you can add nonlinear terms.
Yes.
And you can now start evolving the Schrodinger field using those nonlinear terms.
Yes.
Right? But now you cannot really go back and interpret that as a wave function. Right?
Yeah.
It looks like there's something like that is going on here, right?
So it is not the wave function. That's the whole point. It's a trajectory. So okay. So I was just going to tell you the there is this whole thing called quantum weak measurement. What it does is you couple some qubit or some system to some environment, and you do a strong measurement on the environment. And how you do it is that you first have some coupling, you switch on and switch off. After you switch off the coupling, you do a strong measurement on the environment. And the idea is that the original state will change only a little bit, but you can get the expectation value of something by measuring only this environment. But you can also do the following. You don't need to switch off the coupling completely. And you can, in that case, when you measure the environment, you can control the trajectory or evolution of the other thing. So what they aim to do is that it's something called quantum control. They want to steer the evolution of the original system on some particular trajectory you want. It's often called quantum steering. And the whole point is that this whole trajectory is determined only by this capital A and capital B. There are only two numbers that determine it. And this capital A and capital B is completely determined, again, in turn, by the initial qubit. So in that way, you're not losing information. I'm not saying you can decode the information easily.
This whole difficulty of interpreting this wave function, if you just did, instead of taking a mixed state, if you wrote down the full pure state with this qubit or with this harmonic oscillator and also entangled to an environment. If you wrote down that full pure state, it looks like a mixed state. I think one would see this, there's no possible evolution that wouldn't allow information transfer to the other qubit of Mars. Like let's say I took a qubit, I entangled it with another qubit, I sent the other qubit to Mars. And then I do whatever evolution we're doing. I think there's no way to get this evolution without changing the qubit in Mars. I mean, that's where the linearity constraint usually comes from. It comes from demanding that you take an entangled thing. I mean, this is, there's this Weinberg nonlinear quantum mechanics in Gizon and so on. Usually the constraint, this was where the strongest constraints came from. Now then, you see what you're doing is you're taking a mixed state. You're saying it's a density. Let's say that
no, this is a pure state. This is
in the previous thing you had mixed state, now also you mix. So let's say you take that, you think of that density matrix seriously. It's coming from entanglement of this system that's coupling to gravity and some other system which is sitting on Mars. Now, can you just tell me how the whole system evolves, this qubit and the one on Mars? I think there'll be no way to evolve it consistently without changing the qubit on Mars.
Yeah, I don't fully understand.
So let's write down EPR pair. Let's take an EPR pair. And let's take one qubit of that EPR pair and couple it to this gravity system in the way you like. And let's send the other qubit off to Mars. So now one qubit.
Yeah, if you do the measurement on Mars, it will change the gravitational system.
Coupling my qubit here.
Okay.
I should not change anything on Mars, but this evolution will change something on Mars. Like it will change the qubit on Mars. There'll be no way.
But that is, so you are saying it cannot be a local unitary? No, I can do a local unitary. Why not?
Because it's a state-dependent unitary of this kind. I mean, the whole problem with these.
No, I don't agree. I disagree because, wait a second. I disagree with you because, wait, Subrata, let me answer you. Let me answer. So essentially what you will do, what the black hole will couple to is a reduced density matrix, rho of the first system with any operator O. Oh, sorry, let me call it say X. Okay, let me. So this would be replaced by here. So if I take a reduced density matrix, it will not going to affect the other one, right? Because it will be a local unitary.
Let's write the EPR state first. Let's just write down half 0, 0, 1 by root 0, 0 plus 1, 1. One of the qubits is the one I want to couple. The other is the one which is sitting on Mars. So I have a state of that. You have to tell me how this state evolves. This is a pure state. It is true if I reduce it in the first.
Yeah, you will only, the unitary will act only on one of the factors.
Yeah,
always.
Now this unitary acts differently for the state 0 and acts differently for the state 1. So if I now decide.
It acts only on one of them, not on both. Is the unitary operator is also factorized.
Okay, can we just write down 0, 0 plus 1, 1 be 0.
Sorry, 0, 0 plus 1, 1. Okay. Yes, only this one. So you take the partial trace.
No, you tell me how the full system evolves. Now, what happens to the system, the density matrix of the guy on Mars?
Well, you have to find out how. So you can only say how this. Okay. Yeah, I think you are not able to. So you can say how this density matrix of the first qubit evolves.
Yeah, but you can't have the density. So usually, if you put this into your equation, you find
No, wait. Yeah, but still it's a unitary operator that acts only on one of this. And it depends only on the partial trace. So it will see, there are operators that will appear here, depends only on this. So I don't see any problem. So it will be a unitary operator that changes or acts only on these factors. Yeah. Okay. Okay, maybe because I think for lack of system, I'll come to discussion a little later. Okay, I just want to finish something. So anyway, so I think I'm addressing this little later, but I think there is no issue with this. I don't see.
Extend nonlinear evolution on one qubit to an
but what I'm doing is simply semi-classical evolution, and the same thing can be. So if I take trace, if I take the partial trace of this and measure some operator, and that is the one that appears sources the gravitational side, then what's the issue? I don't see. Well, that had to work out, but anyway, but this unitary is acting only on this too, right?
There's no way to extend this kind of system. I mean, Weinberg had this nonlinear quantum mechanics, and the theorem of Gizon and Polchinski said, there's no way to extend this kind of evolution to entangled states. Because if you try to extend it, and let's say you wrote down U, which depends.
Okay, so maybe you're right. I have to look into this carefully. Okay, thanks. Okay, I have to. There's a good question. I have to look into it then. But I don't see offhand any problem. But at least in this context, but.
Because your unitary depends on zero. It would act differently on the first term and differently on the second term.
But anyways, I think it is. This is in the semi-classical approximation. It should not be an issue. I think this is just. But anyway, I have to look into it. Thanks for this pointing this out. So anyway, so what I wanted to tell you is that this is what I already told about quantum weak measurement. There seems to be something of this kind. But it seems to be that. So essentially, the idea of weak measurement is that you can extract some information of the first system without measuring it. You can couple it to some ancilla, and then you switch off the intersystem coupling, and the coupling has to be specially designed, and then you can extract the expectation value of an operator of the qubit state by simply from the strong measurement of the second system. The strong measurement is usual measurement. And okay, there is also something that you can say that you can control the quantum trajectory. But what is happening here is that we are not here in this context. It looks like a weak measurement. But there is something even more than that, because the decoupling is happening spontaneously. It's not something that we're switching off by hand. And this needs to be revisited in the language of von Neumann algebras to understand why the information can be copied twice. Actually, what you're doing, you are actually copying the information into an output trajectory and in some algebra that describe the black hole ring down, which is stated to be a type 3-1 von Neumann algebra of operators, single trace operators in a time band. Is type 3-1 von Neumann algebra that is claimed to be that's claimed by Leutherer and Liu and Hong Liu, and also by Witten has elaborated on it by using this crossed product description of von Neumann algebras. So this is something that that needs to be understood in this language. And then I think I have some comment that Suvrat is saying, but before that, let me. So in this toy model, what you can do is something even more radical, is that you can not only measure the input qubit, but you can also copy the information of the history of simple measurements, like energy measurements, into the black hole ring down. And the way it happens is as follows. So there will be, this is a way, for example, this initial qubit on the Bloch sphere is encoded, but these functions change as a function of what measurement you have done. So in this way, by the change in these functions, you could measure what kind of history of measurement you have done. If you measure do some simple measurements. So that is something that we are trying to understand better. And there's also something similar to what Suvrat was asking, and that is as follows. So what you can do is that you can take a two-sided black hole, and you can couple an entangled qubit like this, for example, and do something similar. And what you can do some measurement of one of them. If you do a measurement of one of them, of course, there's a collapse there, and typically what you show, there's a positive energy shock and a negative energy shock that comes out, and you can actually open a wormhole. And then there is some kind of puzzle of the kind maybe Subrat was saying. So here, whatever is local here gets transferred here, and so on and so forth. And there is some very strong interplay here, which we are trying to figure out. I mean, this, I don't want to go into details, but it seems like there's some new kind of quantum channels which are normally not thought to be possible, maybe possible. Some new ways of information transfer is also possible. If you look into if you look into this kind of scenarios. So we are trying to understand that. So I think I've finished one part of the talk. So I don't know whether I should go on further because I've already taken up all my time. But maybe I can take 5 minutes and just say something about it, what we are up to, okay? So I'll just try to conclude in 5 minutes. So one of the things that we started looking into to understand why black hole microstate models could be useful is to understand information mirroring. So what happens is this something very similar to this kind of toy examples that I discussed today. So what you do is that there is some reference system which is maximally coupled with a diary. And this diary is very small compared to a black hole, B, and there is an early radiation. And it's important that we are looking at late time or after page time, where you have sufficient number of degrees of freedom in E. So what happens is as follows. So when you throw this diary inside the black hole, there is some kind of unitary that happens. The black hole has some remnant, and there is some small radiation that comes out. It's important that R is very small compared to B prime. So you can argue using the same kind of quantum statistics like argument that Page gave, that after this, if the unitary is sufficiently random, there is no mutual information between R and S. The mutual information between R and S is 0, because R is a very small system, and unitary has basically scrambled all the information in D in the whole thing. So the mutual information between R and S goes to 0. But all the information now should be in R union E, because information is not lost. And so basically the idea is that the information should automatically come out, and this is called information mirroring, and it will take a scrambling time of order RS log SPH. And this is something that has been also discussed more precisely. This scrambling time initially has been made clear in a very nice way by Sekino Susskind, because I think the original Hayden scrambling time estimate was wrong. And right, yeah. Okay, so why I discuss it in the context of black hole complementarity is that if black hole complementarity is true and consistent with unitarity, then we should have some much more stringent requirement in this decoding. So what you have to, because information can be obtained, can be reconstructed completely from the outside, you should be able to decode the qubit without any knowledge of B prime or also U, what is happening inside the black hole. Because initially you throw the diary inside the black hole, this dynamics happening mostly inside of it. So you should be able to decode without even knowing what this B prime is. And there should exist some kind of a decoding map where you can recover the qubit without knowing anything. So I just want to show you something that we have a model that does it without going into all the details, because simply I don't have time. I would just go through and then end. And then there's another thing that we also thought that we should have a microstate model. So one of the things that we did was that when we looked into, started looking at the literature, whether there's some existing quantum circuit or code model where there is a hidden prescale like decoding possible without knowing anything about B prime and without knowing anything about U, where you can write some decoding map or decoding some V operator without, that doesn't require knowledge of U and B prime, for which the black hole is like a microstate, microcanonical ensemble. And there was some paper by Kitaev and Yoshida in 2017 which constructed some hidden prescale decoding protocol, but that requires the knowledge of U. So that's why we thought that why don't we try to make a real dynamical model where we can show something like this is possible. Then if the semi-classical geometry can be trusted, it should be possible to decode a lot of information in D quickly from R with only a limited information of E. And the reason is that, suppose if you believe that this picture that the information has now come out of the black hole in R, and E is very far away because it's very early radiation. So you would think that it should be possible, the information can be decoded readily from here and only some small information of E, not so much. That's sort of a rough picture that we thought of. So we wanted to see if there's some model that can do something like this. So let me show you some pictures without going into all the details. So basically, I just tell you what the model is. The model is simply that we have is a collection of ADS2 throats. So you can think the horizon is discretized into some ADS2 throats, very similar to like what we are having in the toy model, but instead of one throat, you have multiple throats. And then there is some kind of hair, which should be quantized. The hair is something that you should treat fully quantum mechanically. But in the original paper, we just did some classical approximation of the hair, but thinking of it as some kind of coherent state. And if you do that, then it becomes a well-defined model. It has lot of beautiful microstate solutions. And what happens is that if you perturb any microstate, almost all the energy is absorbed into the black hole and nothing goes into the hair. So this is the hair energy that remains almost constant. This is the total energy, and it is simply absorbed by the black hole. And one microstate solution goes to another microstate solution. And then the microstates also have a very beautiful property, which I can explain here. So what happens is this, the hair charges, the hair actually has two components. One component is something that can decouple and live freely, like a hair oscillation in the microstate solutions only. The solutions of the model these are solutions of some equations of motion which is stationary and static. And what happens in such equations is that there's some component of the hair which we can decouple from the entire microstate and live freely on it. And there's some other component which is locked to the with the SL2R charges of the hair. So this is the hair charges that are locked to the interior charges, and these are. So I don't want to go into complete details because it's almost like a randomizing model where these things happen, and then it's a little bit. I don't have time to go through all the thing now. But anyway, the main point is that the dynamics is pseudo-random. If you perturb it, a black hole microstate goes to another black hole microstate, and only in the black hole microstate you can have some notion that you can factorize the two Hilbert spaces into interior and exterior, because the hair in general cannot be factorized into something that is locked to the interior and something is decoupled from the interior. But it happens only when the system settles down into a particular microstate. And this is something that you see, it has an energy absorption and relaxation properties like a black hole. It doesn't, we are not interested in whether we are able to reproduce a black hole entropy here. So anyway, so I don't want to go to the details. So what happens, let me just simply show you some interesting thing of Hayden-Preskel mirroring. So what you're doing here is that suppose you have a 5 microstate model, what we do is that we simply perturb some of this, we throw through 2 shocks into these throats. And then the whole microstate goes to another microstate, and we should be able to decode the information purely from the hair component that is decoupled from the microstate. So far we have not added any Hawking radiation. The throats are not Hawking radiating. This purely classical thing. So in the next, I'll just mention what we are doing with the Hawking radiation now. So now this thing has, so we should be able to decode, but you also need some information of the early radiation, and that is something that's only some notion of something like a primordial frame in which, I mean, this is something that I have to take some time to explain. So what happens is that, so there is some component of Qi prime which is conserved, and that gives you some kind of primordial frame. So that's a primordial conserved quantity, and that's all you need to decode or to find. That's the only information of the early radiation that you need. For the new radiation, you only need to measure there, and then this is the interior of the black hole. But in between, you cannot separate the interior and exterior. Okay, so now let me show you what happens is that this hair modes have some normal modes, and you just look into the different phases of the normal modes. So here, what happens is as follows. So if you take only one single shock, then you see that the phase differences go like this. So first of all, there is some beautiful symmetry. You see, so this is the shock this is a site that has been shocked, and so you can decode which site has been shocked simply from looking at the phase differences of the two oscillations. And you see there is a nice symmetry which is very non-trivial, because neither the initial microstate nor the final microstate has any symmetry. It's a very random state, and both the initial and the final one. But you can still treat the black hole as a microcanonical ensemble and do the decoding. The decoding is completely independent of that. Suppose now you have two shocks, then this is how it looks. Still there's a symmetry. So if you have two shocks, this one is the maximum phase difference was shocked first if the shocks has a name. So this one was shocked first and this was shocked again later. And you see that there is a nice symmetry, clockwise symmetry here, which is again stunning because it's not what you expect. And then if there is something, you can also find it similarly if the two not neighboring sites are shocked. So there is some decoding protocol that you can have. So basically what idea is that you are basically throwing shocks inside the inside your 5-side model, and you have to tell me, the diary is basically telling you which sites were shocked and in which sequence they were shocked. So it's basically some kind of time order sequence, which you can now decode from the phase differences, treating the black hole as a ensemble. So now what you can do, so this is a story for the classical thing. So it looks like there's some Hayden-Preskill like mirroring possible in which black hole complementarity seems to be working. So now if you add Hawking radiation, what happens? Let me now end in just 2 minutes. So you see that all the masses actually go down if the source started evaporating. But what happens to the hair is beautiful. So, okay, so this one of the things is that these zero components will align together. This is basically means that this homogenizing means that you go from one microstate to another microstate where you have basically decoupled. But what happens is if you go for even longer time, not only the throats all go to zero mass, but all the SL2 charges of the throat also align together on a single null frame. So what happens basically is that everything decouples from everything. All the throats decouple from all the throats, and classically all information is lost because all the throats go to a single null frame and everything is decoupling from everything. But precisely this is what you need for information copying, and in the sense that we said. So this is what we're expecting is that when we are able to quantize the hair and study this model, we should be able to see that that the black hole ring down would be able, so first of all, so there will be black hole ring down would be able to copy the information of whatever we are throwing, or as the hair is decoupling from the throat, the information of the hair would be also being copied into the black hole ring down, and then yeah, and so that's what we expect, and this will imprint in turn the information on the Hawking quanta, because as the black hole is evaporating, it will carry the information ring down would be encoded in the Hawking quanta, and you should be able to decode from there. And but the imprinting is complex and conditioned by the history of the microstate. So we are trying to understand whether you can still decode some information without decoding the interior completely, like we saw in the classical model. This is a very non-trivial question. This is where we are trying to understand from Prabha how to learn more about this kind of quantum information tools to answer this kind of question about partial reconstruction without decoding completely the interior from this from our model, which we can explicitly compute. But the decoding of the same information in the hair can also be done rapidly. So if you look now, quantize the hair, you can also decode the same information from the hair, and probably without much of the knowledge of the interior. So this is something that we are trying to explicitly understand the 3-site model. So basically, we are trying to now use these kind of tools that we did for analyzing the very simple toy model, now carry it over here. One, by quantizing the hair, and secondly, by throwing quantum information instead of classical information. So anyway, so I now end my talk because I already taken too much time. So thank you.
Are there any questions? Something I didn't understand was the last part. You went a little fast.
Yeah, sorry.
Yeah, sure. The question is that the way you would understand complementarity, one perspective would be that there is not a violation of the no cloning theorem. No cloning theorem, but rather there's a violation of bulk locality in that two operators which you thought were distinct in the bulk, they seem to be space-like separate, are not space-like separate. Is that somehow?
But that is a problem in general quantum gravity, right?
Yeah, so it's a significant violation of bulk locality in that two operators which you thought should commute actually are the same. So so they have commutator for the one. So you might have thought maybe it's small or something like that, but if you construct complicated enough operators, you can commute it to the order one. I'm not seeing that feature here. it seems, whatever partial reconstruction one does using beat measurement, there is a no cloning theorem as long as.
So here it will be in a very subtle way. So in the sense that, okay, so one of the important things is that we have some non-linearity built in, and that will.
Oh, non-unitarity.
Sorry, non-linearity, not non-unitarity. Sorry. It's a semi-class. It's a non-linear unitary map. You can think in that way rather.
Then there's
Yeah.
no cloning theorem anyway.
There is no exactly. So that is one of the objections that you can have. But what I would like to say is, okay, there are two things I want to say. That we have to understand what happens if you quantize the JT gravity also, right? If you quantize it, and indeed, what is the origin? Whether there will be still some amount of nonlinearity in the full quantum gravity theory that will protect us. So, my answer to that is I cannot comment on that. But what I'm trying to do is in the same philosophy as the Page curve computations, that you somehow trust the semi-classical geometry and see what you can get from there. So that would be my kind of defense. But there can be some, if you want me to like make a wild guess or something, in the full quantum gravity, it could be that indeed, as you were saying, I mean, these kind of issues may have one resolution, that there's indeed no global Hilbert space. Hilbert space is defined by the measurement and the observers. There's probably no like global Hilbert space that every observer can access. And the fact that what you can access is defined by some kind of nonlinear condition implicitly.
Yeah, but you're doing a little bit more than that. So there are two possible resolutions. One of them is what you're saying, that there's no global Hilbert space. But the thing that you seem to be proposing that's in excess of what has, I think, standardly been proposed is that the evolution is genuinely nonlinear.
No.
That's not.
No, this is simply semi-classical approach. This is simply artifact of the semi-classical approach. I simply trust it. You can, of course, say that how trustable it is, and.
Then what one would worry about is that this violation of no cloning is also an artifact of this feature that we got previously, which is that this information was available both in the qubit and in the black hole region.
Yeah.
One could have said that is also
very good.
An artifact of the semi-classical.
Yes.
So once you get away from that, you lose that feature.
So my response to that will be, people have been studying such nonlinear maths before in the context of qubits coupled to some cavity QED and all. There it doesn't happen. First of all, there's no decoupling that happens. And the fact that you get two kind of quantum trajectories after the decouple, that information is copied twice, this is also something that is quite novel. I don't think people have seen it before. It's quite important that you have a black hole-like system and you have some locally, if not globally, some kind of semi-classical approximation. So that's only my defense. But you're right. I mean, in a way, it is not like there's any surprise, because we don't have a linear unitary map. So yes. Yeah. Yeah, so in some way the information is being copied into some kind of algebra or some quantum trajectory that the black hole is, or some kind of trajectory the black hole takes. That's true. That is classical GR here. Yeah. So, okay, so the point is that here, the point I am taking is that this, so if you look at it, algebra operators that describe this geometry in a time band, that's like a type 3-1 algebra. It's a algebra of single trace operators in this time band. So from here, you should be able to recover. I'm not giving you a decoding protocol. I don't tell you how decoding is possible yet, right? This is something that we are working on, but I don't know. They're simply saying that it's encoding it somehow. But the decoding is a totally different thing.
So I have the information about the profile of your probe that I took from the boundary, and the same information can be partially incorporated in the polynomial.
Here it is completely, actually, in the case of quantum. So if your input Hilbert space and the output Hilbert, if your input, so in the case of the qubit, the input and output Hilbert space are the same dimension. In the case of the quantum harmonic oscillator, the output Hilbert space was larger. So the initial qubit was thrown in some kind of quantum trajectory in the larger Hilbert space, and there was no loss of information. There was also no loss of information in the black hole ring down. You could decode it completely. Both the block and this.
Just about the quasi-normal.
No. The whole point is now in this model, when you now allow the black hole to evaporate, the ring down will be imprinting on the Hawking contours. So that's the idea. That's the thing. But it's also copied into the hair. The point is that from the hair, you can decode it quickly without knowledge of the interior. But it's not quite clear to us yet how this decoding from the Hawking radiations. So we are studying this decoding now. So because you cannot, as you write, we don't know how to measure in quantum gravity. So this is simply a statement that M of U is ring down, but we cannot really, M of U and M of U prime doesn't commute in reality, right? But so in the semi-classical approximation, the best you can do is to make the Hawking radiation happen and try to decode from the Hawking radiation. This is something we're studying now. The hair we understand. The hair we can decode completely without knowing the black hole interior, but it may not be true. But maybe you can decode it. Maybe there's some coarse-grained information you can still decode from the Hawking radiation without knowing the interior completely. So some of the questions that you are asking, maybe we are trying to think if it can be addressed, like to what extent, to what extent, there is this there's this notion of a global Hilbert space Bakeground or something like that. Yeah.
To me, at least the most serious issue would be to extend the evolution to these kinds of without violating like locality. If one can, I mean, this is the main problem. Maybe one can.
Well, we are doing something like that here, and in this case, actually, because of the wormhole opening up, there is always a wormhole that opens up here and affects the. Yeah. So here there is always something like a wormhole that opens up. That's what we have seen. Because if you measure here, do some energy measurement here, you automatically do a measurement here. And what is happening is that there is one positive energy shock and a negative energy shock that comes in. And that opens up the wormhole here. Yeah. But yes, I mean, in that sense, but you can consistently describe this evolution. There is no, as far as I don't see there's any problem. But maybe that's the answer to your question. There has to be some subtle wormhole, or I have to think about it. In the original context of your question, I don't really understand the real problem, but okay, yeah. Yeah, thanks. I have to read the Bison-Ponsis paper then. Any more questions? It's time for the nice one. Thank you.
Yeah, and I can explain to you.